Good evening. Welcome to the webinar and town hall meeting about the ethics of artificial intelligence in CP research. My name is Paul Gross. I'll be your host, and I'm very happy to have Dr. Zach Vasoulis with us tonight. I'm going to take you through the CP Research Network quickly. Let Dr. Vasoulis update you on both an educational talk and about an updated study that we have submitted, but really want to get your input about the ethics as you see it of artificial intelligence being used in CP research. Okay, so there was a 2014 NIH meeting that established the need for a national registry to compare the effectiveness of interventions, to study adults more, because kids were studied mostly, to develop a basic and translational research agenda, bring more young investigators into the field, and to create closer connections between patients, families, and investigators. So those objectives ended up being the impetus for creating the CP Research Network. And we were founded with a mission to optimize the lifelong health and wellness of people with CP and their families through high quality research, through education and community programs. One of the first things we did was we had a group effort to set a patient-centered research agenda. We got together in Chicago in 2017, subsequently published a paper, and that's really driven a lot of our work. So our vision is that by engaging all of you and a large number of health systems in what's called a learning health network, a group of hospitals that use the data from care to improve care, that we can collectively focus the research and the care to address the things that people with CP care about most. Participation and quality of life came up as the highest things in that research agenda. And then by getting you to share your lived experiences and measuring the healthcare system, we can continuously improve the health and well-being in ways that are important to the community. So some milestones in the education space. We started with our CP toolkit. We went on to launch MyCP to have personalized information. And then we have been running these monthly webinars for several years now. On the research front, we did launch that clinical registry and a community registry, so that national registry. I see I didn't update this slide. We now have over 15,000 patients in our registry. We did our patient-centered research agenda that I mentioned. We went on to get significant funding, in particular in the area of translational medicine. We have active quality improvement initiatives within the network to improve care. And then we're actually up to 18 publications and over 50 academic presentations. We're very actively sharing the findings with both the healthcare community as well as the community at large, and using that registry to make for more discovery and to support getting additional grants. And then in wellness, as many of you know, we're partnered with the National Center for Health, Physical Activity, and Disability on the mentor program to improve health. So quick data point, gross motor function classification system is a really important measure of how people get around in the community. Here's a data point from last year. You can see the distribution of our very large registry of GMFCS, and then you can see the distribution of age, where about 26% of our people are adults. If you look at the community registry that captures data not from people coming into the hospital, but from people just answering surveys, you can see it's a very different distribution of GMFCS, and that it's many more adults are involved in our research. So we are spread across the United States. We're up to 35 centers. The green circles are lifespan centers. The green pins are sites collecting data into the registry. Yellow pins are sites working on the technology. Red pins are working on agreements, and blue pins have raised their hand and said, we really want to do all this, but we have got to find the funding and get through the agreements first. So our strategy is one of letting 1,000 flowers bloom and really sort of stimulating the ecosystem. So we started with that patient-centered research agenda. We build infrastructure to help the community and the clinicians define meaningful questions and answer them quickly. we build either evidence, i.e. research, or we improve care through quality improvement to change outcomes. And then we use the registry to monitor both the implementation of that care as well as the outcomes. So we use a process, a standard operating process internally for how we approve new studies that start with people brainstorming concepts, moving through an approval process, going and getting funding, executing, and then publishing the knowledge that's learned from those studies. This is an animation of how this infrastructure that we have built has progressed over the years. So the pale white are child studies, the hot pink are adult studies, the gray are lifespan studies. So you can see the network's been very active and it's produced a lot of new ideas, new learning. So in the end, the CP Research Network is quite unique in that the way it connects the electronic medical record is a great way to avoid the duplicate data entry of past research networks. It can tie in patient-reported outcome measures or PROs to that clinically validated data, and it supports hypothesis generation, so for research planning, as well as identifying practice variation, which is really important both for research and improving care. And it creates this platform by which we can do continuous improvement. And not only can we do it continuously, we can really look at long-term outcomes because of the way we're capturing information. And that is how we implement a learning health network for CP. So that's my very quick overview, a little bit repeated just because I didn't have my slides up. Thank you, Dr. Vasoulis. So let me turn it now to Dr. Vasoulis.
All right, thank you, Paul. And thank you everybody for coming this evening. Some of you may have heard a variation of this just about a year ago in January. But there's a lot of updates and new exciting things, so hopefully it doesn't seem too repetitive. All right, so I'm going to talk a little bit about some ideas and projects that we've been working on. I'm going to start first with why we're even doing this. So I'm a pediatrician, I'm a neonatologist, and my role professionally is to take care of babies, but it's also to talk to their parents. And there are questions the parents have. Sometimes they say them out loud, and sometimes they're just in their mind, but they're really important questions, things that they care a lot about. And they wonder, especially if their baby is born early or if their baby is very sick or both, will my baby survive? How long will they have to be in the hospital? And then what is their life going to look like once they go home from the NICU? Doctors also have these questions. Ours are often driven much more by the clinical problem that's immediately in front of us about the right treatment that we should be doing in the particular moment. But we also wonder about complications and problems in the long run. And then how can we prevent it? Are there things we can prevent and how can we prevent it? And then, the neurodevelopment is at the top of our mind for both the parents and for the folks taking care of the babies. And this is a really interesting paper. It was published more than a decade ago now from some parents in Canada who had 25-week twins. Their babies were very, very sick. One of them unfortunately passed away in the NICU. And another one had a MRI term equivalent age, which is a fairly common practice in many places in North America and in Europe. And they saw some findings on the MRI, and they sat the parents down and told them that they were worried about neurodevelopmental disability and cerebral palsy as a risk. This is a baby that has not even yet gone home from the NICU. So and this is 2012, so early detection was not even a thing at that point. But even the best early detection programs are not operating in this time frame. So both of her parents had PhDs. They were scientists, but not in medicine, in other areas of science. So spent a lot of time reading things on the internet, downloading articles, and worrying a lot about their baby, who's named Marin. And then when she came back for follow-up, and these are actually pictures from the article of her, both as a baby in the NICU as well as at age 4, she had typical neurodevelopment. But I think the story really underlines how challenging making predictions for parents in the NICU really is, how fraught that problem or that process is, and how we just are really not good at it. I think if any neonatologist is being honest with you, they would tell you how little we can predict. So part of this is a function of what's happening with the brain. This is a great picture that was it's 3D reconstructions of the brain taken from MRIs that were captured over a whole period of the NICU stay. And you can see a baby born at 25 weeks, just like the babies in that last slide I just showed you. Their brain is completely smooth. It is small and completely smooth. And all the development that happens, the brain increases enormously in terms of its actual size and the complexity, all that folding during the third trimester, which is the period of time most preterm infants are out in the world. That still happens, whether they're in their mom's womb or not. And injury to the brain, which directly affects the brain, or indirect injury, which comes from things like poor nutrition or inflammation or infection, other problems like that, can influence how this brain develops. People have come up with a whole bunch of different systems to try to predict outcomes from MRI. And all of them, pretty much across the board, have a pretty good negative predictive value. So that means if there are no problems seen on the MRI, then that is a pretty strong indicator that that child will go on to not have any neurodevelopmental problems. But they are terrible at positive predictive value. As soon as something shows up on that MRI, whether it means something or means nothing, that's where we really don't know. So based on that, the American Academy of Pediatrics actually published an article, routine term equivalent MRI was considered wasteful spending at that point, and actually they strongly recommended against it. That has been heavily debated since that time. That was about 10 years ago. But it certainly calls it even further into question how much information can we get from the MRI and how accurate of a prediction can we make from it. So right now, not surprisingly, there's huge variation from hospital to hospital. Some hospitals get no MRIs, some look at different risk factors for babies and decide to do MRIs, and others get MRIs on every single baby. Right now, the standard practice is that a radiologist sits down and looks at pictures like the ones on the screen here, subjectively interprets them, and writes up a report. That report is read by either a neurologist or a neonatologist or both, and they use that information to sit down and talk to the family. So there's a lot of layers. It's a little bit of a game of telephone. And you can imagine there's many opportunities where information is lost between when the scan is done, the radiologist reads it, the neonatologist or neurologist interprets it, and then talks to the family. And all these research tools that I was just talking about are way too complicated to use. Nobody uses them clinically. So it's just this entirely subjective process. So now I'm going to talk a little bit about AI. How can AI help us get through this problem and come up with something more meaningful? And AI certainly comes up in the news an awful lot. I'm sure you all hear it read it in the newspaper or online. But it's actually been around a lot longer than I think many people realize. Here's some examples right here. So the Postal Service for 30 years has used AI to recognize people's handwriting and figure out what the zip codes are to properly sort mail. Deep Blue, those of you that are older probably remember this story. You know, the supercomputer made by IBM that beat Gary Kasparov, the famous chess player, back in the late 90s. Tesla cars now contain quite a bit of AI technology that help them to sort of self-drive, not fully, although that's its own debate. And then Eliza, this is a computer program from 1966. So this was an AI that was developed to function as a psychotherapist. People could sit down and chat through their problems with the computer, and it recognized language when you typed it in the computer screen. So how do AIs actually work? And I guess if you're coming up with a recipe for how to build an AI, it takes four ingredients. So the first one is data, and that is in a lot of ways, the most important part of the process. These systems all learn. They learn from examples just like we do. We learn from hearing the same spelling words over and over again, or doing the same activity, practicing it, practicing the piano or something to learn. Data is that fuel for an AI. Algorithms are the code that makes sense of all these data, that try to put rules on top of the data to make meaningful decisions. The models are, in a sense, the brain of the system. It is all the algorithms put together, and it is the result of all of the training. And this model can be picked up and moved somewhere else and used for a new task. Even though it learned on pictures of fruit, like I have in this example here, that same algorithm or that same model could be used to predict pictures of pets, for example, cats versus dogs. That's something called transfer learning. And then, of course, like any robust system, training and validation is really important. It's not good enough to make it. We need to verify that it is functioning the way that we expect it to. So in this example that I'm showing right here, we are training a machine learning algorithm to tell the difference between apples and bananas. And so if we show this system example pictures of apples and example pictures of bananas, it eventually will start to develop some rules. This is a really simplistic example where the rule it has figured out is that apples are always red and bananas are always yellow. Now, of course, that's not universally true, but for the sake of example here, those are the rules that it has learned, and that's what's internalized inside of its model. Um, so this takes us to the next step about how this training actually happens. And there's two different forms of this. So one is supervised learning, and that I think is the most intuitive and the way we expect AI to function. And that's where we label it in advance. When we are giving the computer all these pictures of apples and bananas to learn from, we actually are saying to the computer, this is a banana. And then we show it a picture of banana. And then this is an apple. And we show it a picture of an apple. And it learns from these labels from an expert, us being experts of what are bananas. It learns from those examples as it builds that model underneath. Now, there's another kind of machine learning or AI where the computer figures out the labels itself. We don't tell it anything. We just give it a whole bunch of pictures of fruit and it examines them and it starts clustering them. It has absolutely no idea what a banana is or what the name of a banana even is, but it can tell over time that there's a whole bunch of these pictures that have this yellow curved thing. And these other ones have this red round thing. It doesn't know what those are, but it knows that they are different, and it is clustering the two of them. Um, this unsupervised learning we have found can often be much more powerful at doing these prediction tasks because it's much more flexible. It's not bounded by the labels we put on it. It came up with the labels on its own. So, for example, if we give it a picture of a peeled banana, which is still a banana, uh, it'll pick that up because it resembles in many ways what a banana looks like, and it can get over the fact that it's not exactly the same compared to a supervised model, which might struggle with that. So just to give an example, this is a project that we did a few years ago where we tried to improve an image scoring system. This is something we use to predict outcomes for babies. This is an MRI system that was originally developed at WashU for babies with hypoxic ischemic encephalopathy, HIE, also called birth asphyxia sometimes. And so in this particular project, we had a whole bunch of MRIs that were done on research patients. And one of our faculty members, Shamik Trivedi, came up with a scoring system. And it's really complicated. It compares the right side and the left side, and it looks at all the different sequences in the MRI and all the different parts of the brain. And I added it up, and there are 81 different things that somebody has to look at on the MRI to come up with a score, which is a lot of work. It's a very good system. Nobody uses it because it takes too much time and it's too complicated. My thought was that we could use AI, especially that unsupervised learning, to comb through all of these different things and figure out which components actually mattered. My thought was that many of these are duplicative of one another. It's not telling us more to see it in, several different sequences, for example. And so we put all this into an AI algorithm, and this is what we found. So there's a whole bunch of different types of models here. The deep learning model, the AI model, is this one all the way on the bottom, and it had 85% accuracy. I got the answer right 85% of the time compared to the original model that only got it right 40% of the time. But not only were we double the accuracy, we only needed to know three things. We cut it down from 81 to three and had better accuracy as a result because we discarded all the things that were extraneous. They were not necessary in the model. And we could have better performance focusing on the things that matter the most. And that's one of the most powerful ways of using AI is to really help us focus. The data registries like CPRN, for example, are enormous. They have so much data in them, and it's overwhelming for somebody looking at it to try to figure out what's the important stuff in there. And AI is a tool that we can definitely use to help us focus our attention on what matters. We have to be careful though. AI, computers are lazy just like people are. This is an example from a couple of different studies that were published where they were trying to use AI to help them recognize, and the top one here, help them identify pneumonia. So they gave it a bunch of chest X-ray pictures and asked the computer to learn which patients have pneumonia, which patients don't have pneumonia. And when they trained it, they found out it was really, really accurate. It was very impressive performance. It got it right almost 100% of the time. But then they had it add something called saliency maps. That's basically asking the computer to highlight in red what part of the image did you pay attention to when you were deciding whether this was pneumonia or not. And you would expect it should highlight the lungs because that's where pneumonia is in the lungs. But every single time it highlighted this little marker. And for those of you that don't look at a lot of chest x-rays, the radiology techs, when they take a picture, any kind of radiology study, will put these little markers on there, mostly to tell, in this case, that's the letter L. That tells you that's the patient's left side. So you can tell the left from the right. So they put this little marker on there. It shows up on the x-ray film. What they figured out, the reason this was so accurate and the reason the computer was paying attention to it is that the markers that the radiology techs use are different. If somebody is admitted to the hospital, in which case they use this the circle one with the black background. And if it's an outpatient, like it's taken in the emergency room or it's just taken as an outpatient in radiology, it doesn't have that circle around it. It's just the letter L, and it's a white L instead of, it's a bold white L instead of a faint white L. And so the computer figured out that somebody who is admitted to the hospital probably has a greater likelihood of having pneumonia. They're admitted to the hospital. It doesn't actually need to pay attention to the chest x-ray at all. And it used this as a shortcut to figure out who is admitted to the hospital and who isn't. The same thing down at the bottom here. This is from an algorithm that tried to identify COVID on a chest X-ray. And so you would expect it should look like this, the blue boxes right here showing, the findings in the lung, that the AI model should pay attention to where COVID happens. But when they looked at many of the examples, the places that it was saying important were all at the edges. And in the edges here, that's where you can see the chest X-ray is kind of cut off on the screen. You don't see the whole lung. And that happens a lot on chest x-rays that are called portable x-rays, where the x-ray machine is brought to the patient's bed rather than them going down to radiology. And it's hard to get the alignment just right on those. And so the algorithm recognized that these are all portable x-rays, which are probably taken on sicker patients. That's why they're getting portable chest x-rays. And they are more likely to have COVID. So this is all just a warning that AI often takes shortcuts, just like humans do, to get a better performance. Okay, so this project that we're going to talk about now is really bringing all of this technology that I talked about and this problem of prediction, making early, accurate, reliable predictions. Um, and some of this is really about the amount of data that's there. His MRIs contain millions and millions of individual pixels, little pieces of information. And that's more than any human can perceive, no matter how good of a radiologist you are. These research tools that I talked about, these research scoring systems, shouldn't be limited solely to the domain of research. Their ability to predict outcomes should be something available to everybody. It's really an accessibility problem. And there's a lot of value in making predictions using what I call a whole person model of data. So MRI is part of somebody's story, but it's not their whole story. The information that's in their medical record is part of their story, but it's not their whole story. Genetics is part of a story, but not their whole story. So the idea is that if you fuse all of these pieces together, you get much closer to describing a person as a whole rather than just these individual pieces. So it's a better prediction, and it's also doing much more justice to a person as a whole rather than just a discrete element. So in a CP related context, we think that these systems, if applied correctly, can predict ambulatory outcomes, for example, and I'll talk a little bit more of the outcomes in a minute, more accurate than what we already have out there. So as Paul mentioned, we submitted a grant to the NIH um, in February, earlier this month, to try to fund these efforts. And there's three aims to this project. So the first one is to use these tools to improve our predictions. And there is already a CPRN imaging registry underway right now. That's another project where we are trying to build an imaging registry alongside the clinical registry. And so as that grows, that becomes a great resource for this project. And we want to use that unsupervised learning that I talked about, where we have the computer find what's important in the MRIs, not our biased human view. There are ways that radiologists read MRIs. We don't want to start there. We want the computer to start with a blank slate and find what is important in those MRIs that help cluster patients, whatever those clusters are. And then the second part is use supervised learning. So once it has come up with these what are called features, so in the computer science lingo, variable, I think is another word you could use for it. Just these different aspects of the MRI that the computer thinks are important for making predictions. We, in the second part, will use supervised learning, where we will say outcome related information to try to map these things together. So we'll try to come up with a way to predict these multi-class outcomes. So this includes GMFCS, MACS, and then also topographical distribution of motor symptoms. So trying to map brain findings to the output, so the whole way through. The second part is all about that multimodal prediction. So this is this whole person model of data, trying to fuse all of the different parts of CPRN together to maximize both accuracy and then also early timing. So it is important to be accurate, but it's not helpful to have a model that predicts GMFCS by the time you turn 18. You want to know that before you turn 18. So prioritizing earlier but also accurate information. And then the final part is to share this. So this project would create a framework, a toolbox that could be used for other chronic conditions that are similar in many ways to cerebral palsy, where it's some combination of genetic predisposition, environmental exposure, and then discrete injury episodes, where it's sort of all of those together. And so this could be used to help many people eventually. What we need from a CPRN is a couple things. So as Paul mentioned, there's 15,000 patients in CPRN now. We think that there are probably at least 5,000 MRI scans available, at least from those patients. The exact total number is something that we're sort of in the process of figuring out. Dr. Galliano-Morel's project that I mentioned is all about building this registry, and that's underway right now. So we are participating in that too. We have the software already installed on a computer, and we're ready to start pushing those MRIs, as are many other sites, I think. This obviously involves matching data from the registry to the imaging to build these models, to have that fuel for the algorithms to learn from. And then, of course, we need to figure out exactly how this is going to work operationally from a compute perspective. So this has been a bit of a journey for us. The first thing that took longer than we expected was find somebody at the NIH who was interested in machine learning as a real project rather than just as a buzzword. There's a lot of interest in the concept, but very little expertise, or at least back at the time that we were originally talking about this. That may have changed since it's actually been a little bit of a little while. Collaborators are very important for a project of this scope, and I was fortunate to find some folks both here at WashU as well as those at University of Pittsburgh where the data coordinating center is, who bring expertise in all these different domains to make this possible. We submitted a grant back in May 2024 through a mechanism called OTA. The underpinnings don't really matter as much as it's just an NIH grant. Unfortunately, we were not funded with that one, although the feedback was very positive and we were encouraged to resubmit it, which we just did earlier this month. So this is sort of the timeline of where we have been and hopefully where we are going. This imaging registry, as I mentioned, is in the process of being built out right now, and hopefully will be a robust source of information by the time we're ready for the project to start. So I think that's it for everything I had for slides, but I'd love to hear people's thoughts, questions, ideas um, on this topic.
Yeah, Zach, if you can stop your screen share, that would be great. So people can, so we had a set of questions that I think are in my last slide after what I presented. So I can drop the questions um, into the chat, but we really want to hear from you. I meant to actually say this before I turned it over to Dr. Vasulis, but I was running behind, so I kind of got a little messed up. But so I'm going to drop these questions into the chat. And so the question is, what do you think about each of these things? And so if anyone has a comment, they can either raise their hand, or if no one's speaking, they can speak up. So let me drop them in. So anybody have any thoughts about, like, so the study, we love to hear about the study, but we've presented sort of this is an iteration. What I really want to understand is how you're feeling about the concept. Do you like go team, or are you like, this is really scary? Um, you know, I'd rather have my doctor make a prediction based on less knowledge than, this thing that's machine aided or whatnot. So what are people have any thoughts or comments? Go ahead, June.
Hey, I think it's very exciting. And of course, I have questions about all the pesky details about verifying. But I just wondered, given the chaos that's going on out here with everything in NIH, are you optimistic about funding, or do you think that's going to slow you down in that process?
Zach, I'll let you take that one first. I'll make another comment.
Sure. That is a fantastic question, and one that I don't know that I have an answer to yet. I think it's still a little early to know how the funding landscape is going to change. Um, as somebody who is very interested in child health, I would hope that that has a universal priority regardless of where people are coming from. But I don't know that for sure.
The thing I would say, so, I'm very concerned with some of the proposals that haven't been enacted yet, but there's been, indications for that it'll have a downstream effect on the CP Research Network. A lot of our funding comes from the hospitals wanting to contribute data to make their research grants stronger. And then additional money comes from the grant funding. Um, and so I am concerned that we will have to get smaller as I am watching what's happening. And that's a concern. I've asked a number of our most senior people, like, what is the word within their organization? I say some organizations have already frozen their spending and their hiring. Some have actually moved towards making cuts just anticipatorily. And mostly what I hear people saying, like, let's wait and see. Medical research is a bipartisan issue. It's strongly supported. Many of these changes will have to move through the different branches of government. So let's wait. So let's wait and see. So personally, what I'm doing for CPRN is trying to make sure, A, that I raise more money from other sources, B, that the investigators know about other funding opportunities, in particular, some small private foundations and also PCORI, which shouldn't be affected by this. But there's quite a bit of wait and see. And there is some very real things that have happened. Like, we've had multiple grants that were due to be reviewed by a study section, which is the way the NIH works. And we were told that study section got canceled. You'll be reviewed at a later time. The reason why I wanted to do this ethics talk is I am on an NIH panel in 3 weeks, and I wanted to have community input, not just Paul's opinion about the ethics of AI. And that's maybe not going to happen. So we'll see. So it's going to slow things down for sure. That's what I would say for now. Amber, I think your hand was up next.
You're on mute.
Sorry about that. Yeah, I think it has a lot of potential. I mean, good and bad, as all technology. My question would be, I guess, would the clinicians and researchers and all of us still be still looking at things? Because, for example, I had a doctor who never wanted a radiology report. He's like, I don't want it. He goes, I'm going to look at it. He goes, and then I'll read the report after. So that's, I guess, one of my concerns. Although I think AI will add to that if people are still really going to look at things and not just go by what AI says, like some people do with radiology reports. Actually, a lot of my medical professionals that I've seen do that, and it was only that one that I was like really impressed. Like, he's like, yeah, I don't want that. So what are your thoughts on that? Because I think it could make us more lazy, I guess, is what I'm alluding to.
Yeah, I think that's a really, really excellent point. And some of this is going to be driven a little bit by the regulatory environment for it. The FDA has been kind of all over the place on regulation for AI. Initially, they classified all kinds of computer software that is AI as a medical device and would have to go through the very rigorous pathway that any medical device does. And then they got a lot of pressure from manufacturers, so they swung a little bit back the other direction. But at least right now, there is no AI system that is independently making decisions. So the place in radiology, to use a specific example, where AI is used commercially right now is in adult stroke detection. There are actually 3 or 4 different companies that make software that feed CT scans and MRIs into it, and it analyzes the image, finds the stroke, and then points it out to the radiologist. A radiologist still has to review it. They still need to sign off on it and write a report. So it's not independently operating. But the idea is that it helps them to work faster so they can read scans faster to get the information to people more quickly. And I think at least for the near future, that's how all of these things are going to work. They're basically assistants for the doctors. They're not replacing them. And that's sort of where the environment is. these days. But you're right though. I think there's the potential of people becoming overly reliant on that technology. Although, I think that that happens in a lot of areas. I mean, I guess I'm getting old enough now. I find myself saying that to our trainees, that's, oh, back when I was just a kid, I did that, backwards and in the snow. And so I think that that's sort of a natural human reaction. And sometimes, the some of the fundamental basis for this is just how much can one human process at a time. And the bigger and faster and more complicated a NICU gets, or any hospital environment gets, the less one person can do. So if a computer can take some of that load off of people and allow them to focus on the things that really matter, I think that's actually probably a net benefit for everyone. But there is definitely a balance to be struck there for sure.
Great. Thanks. Paul, before I turn it over to you, I'm going to take a question from the chat. Jim Dobbins said, especially since this deals with children, how are their identity and privacy protected?
Yeah, that's a great question, and something that the clinical registry, and Paul can speak to this even better than me, but it's built into CPRN sort of from the ground up. This is a de-identified registry. The MRIs, when they come out of the scanner, have a lot of what's called metadata. So it has this separate file in it, basically, that says the name of the patient, and their date of birth, and their address, and all that kind of stuff. And there are very good, robust tools for stripping all that information out. So it is just the pictures only that go across. We in this grant, I didn't touch on it, but one of the things that we are working on is what's called a privacy protecting linkages. So it's a way, even when you have the same person that's been seen at multiple hospitals or may have data coming from multiple sources, can all be linked as the same record, the same person underneath. But it's protected the whole way through. And it's a very, very sophisticated way that that's done technologically, but it's all designed um, to work that way to preserve privacy. The flip side, and I realize I'm giving way too long of an answer here, but the flip side is the AI can also be used in reverse too. So AI is very good at solving any sort of pattern recognition is really where it excels. That's what it does. It finds patterns in things and classifies them. And so there is a concern that AI can be used to reverse these privacy protecting things, that it can, in a very smart way, relink stuff in the background. That's I don't think there's any examples of that being done at scale in medical information. And I think financial targets are probably more worth their time than medical information. But just like we've sort of been talking through this whole presentation, there's good and bad for everything.
Thanks. Just because Susan Paserno mentioned it, I do want to say that in the last aim that Dr. Vasulis was talking about making an open framework, while our target for this is, neonates and their MRIs and prediction of outcome, this can be applied to adult, aging issues, adult health issues. Like it is really like the ability to demonstrate that you can read MRIs with greater precision and combine it with other data to learn what might be predictive of cervical spinal stenosis or whatever. There's so many things. So, Paul Staunches, you were up next.
Yeah, I'm just gonna quickly comment on each of your bullets here. AI in medicine, no surprise here. I'm all about it. I mean, it's a tool. I've been using AI day to day in my activities.
Mhm.
Generating an email helps me. I
Mhm.
type in 2 sentences, I get 3 paragraphs.
Mhm.
To see that ability for a doctor or clinician to be able to take to magnify their work exponentially is very exciting.
Mhm.
And I absolutely do believe our data should be used However, putting the proper guardrails in place for data privacy, the typical guardrails you hear about mentioned with responsible AI, using AI responsibly. I do work for Microsoft, so these are all buzzwords for me. So, putting the guardrails in place. Again, my child's data. I'm talking about myself. If it was my child, I'd be the same way. If we could accumulate this data and get more out of it, we should try to do so. Should we be consented? Yes. Not now. The only detail I would get into there later on would be, do you get consented for every single study that goes on to that against that data? I don't know. I mean, ownership of data, it's kind of a shared data, right? I mean, it's data about me, but it's taken, I'm not going to answer HIPAA questions. I'm not a doctor, but there is something to be said for that. I think what can researchers or industry do with it? I think let your imagination go out. It's how much can we think to use it for, as opposed to what can we use it for? Because the more you work with AI, the more you realize you just said you started, you prompted with a little bit. You say, "Oh, well, I meant to ask you about this specific aspect," and you start going down into the data that's really interesting to you. So I don't really have any questions as much as those are my comments. I'm all about it.
Great. Thanks, Paul. I'm going to take two questions from the chat before I go to you, Duncan, just because of when they came in. I'm going to take Christina's question and say, absolutely, it can be applied to gait analysis. And in fact, I was on a call with Dr. Wade Schrader and Dr. Jim McCarthy from Nemours and Cincinnati Children's just today, talking about work that's being done in that area. And that we're looking at how we could do more. So absolutely. And then John Borland said, and I want to get your comment on this, Zach, because what you're talking about kind of challenges this at one level. It's good if it can be made accurate and is monitored, verified by experts. And when you have this level of detail that the expert can't actually see, how do you feel like that will happen?
Yeah, that's a great question, and I think there's two parts to that answer. So one, and this is very much in process right now, as people are publishing AI research in scientific journals, it's really important that those papers be reviewed by people that know the field. And like any new field that starts out with very few experts, that's hard to do. I mean, the people who do it know all the other people that do it, which is fine. But we need to make sure that it's not novices that are trying to judge a paper, because it's very easy, like any statistics thing, it's very easy to mislead someone with the results of an AI project. There are some guidelines and frameworks that are being developed for standards. I think one of the things that's really important, well, there's two, just to sort of answer it quickly. One, when you're presenting an AI model, it's really important that you present far more simple models in comparison to it. So if you can get the same result from a really simple model, there's no point to using the AI. And then the second one that's really important is validation. I've seen figures in the past where it's like 90% of the publications about AI are people talking about the model for the first time, and nobody ever follows up on it with other data to see if it is just as accurate when applied to a different hospital or a different network. So that's really important. And then the second part is sort of this behind the scenes thing with this deep learning, what the AI algorithm is finding in these patterns. can be very opaque. It can be very hard to know what it thinks is important when it's looking at an MRI scan. But just like any technology, it improves. So there's a lot of tools that are available now that help the AI to explain its thinking. Why does it think this is important? Why is it choosing this as a predictive factor and not that as a predictive factor? And those tools are just only going to get better.
Great. Thanks for that question, John, and answer, Dr. Vasilis. Duncan.
One comment and one question. You did indicate that at this point, the clinicians aren't making specific decisions about treatment based. It's kind of interesting because it's my observation that the insurance companies are already making treatment decisions based on AI. So it appears that the insurance companies are a little bit further ahead in terms of definitive decisions. And then my question is, AI obviously recognizes patterns, and is there at this point, you talked about an MRI registry, is there a critical mass in terms of the numbers that we need to move into a position where we can make some definitive predictions about treatment?
Yeah, those are both excellent comments. And I 100% agree with you. The insurance companies are way ahead on this, mostly because they don't have the same kind of regulations that medicine does. So that helps them quite a bit. Although dangerously so. They've been caught a number of times using AI algorithms with some pretty significant bias issues. And making bad decisions based on those. So moving slower and making sure we're doing it right, I think perhaps has some advantages. The second question is one about sample size. How many do we really need? And that is an excellent question and one that there really is no answer for. In conventional statistics, there's this idea of a sample size calculation. If you know how big of an effect you're looking for, you can do some math to figure out how many patients you need to detect a certain difference. That doesn't really work with AI. I mean, one thing we do know is more is certainly better. The more examples you can get for it to learn from, the absolute better the predictions are going to get. And at a certain point, you saturate it, that once you get over a certain number of examples, the accuracy doesn't get any better. But where that threshold is, we're going to have to do it to actually know that.
Great. Thanks. All right. Well, actually, we're at time, and there are a few more questions, one of which that I think is, well, there's multiple questions. Dr. Vasilis, if you have a couple minutes, we'll go. If not, I know it's later where you are than where I am.
Yeah.
So there was a question from Dr. Debbie Thorpe. As clinicians have seen kids with grade 4 bleeds that are globally devastated and others with level 4 bleeds that are ambulating, pretty typical cognitively. So if going by MRI alone to train AI predictions, what percentage of the correct long-term outcomes would be missed? So can you comment on why you don't think that'll be a problem?
Yeah, and I think that is specifically because of CPRN and the longitudinal nature of the data. A conventional pediatric or neonatal research study, the gold standard is 2-year follow-up, which is way too short of a follow-up to have meaningful long-term outcome predictions. That's mostly just a mechanism of how research funding works. We can't really do it longer than that. But CPRN data goes through adulthood, through childhood and through adulthood. So when we are training the algorithm on MRIs, we're trying, we are emphasizing as early a prediction as possible, but with a certain threshold limit of accuracy. We want to get it as early as possible while still maintaining that accuracy. And And we can, we talked about this sort of as one monolithic model, but it doesn't have to be. There can be one model that is very focused on broad outcome groupings for a very early prediction. And then it can be a lot more nuanced if we're talking about outcomes at school age or outcomes at puberty, for example. And we can use all this information we have in the data registry over childhood to train it against those outcomes, not these really early inaccurate 2-year outcomes.
And I would add that part of the richness that we have is not only the longitudinal aspect, but it's the fact that we have all these different dimensions of data, your sort of whole person of, all of the treatments that they receive. So you could have 2 kids born into the NICU with the same level of intraventricular hemorrhage, but then see what's different about the person and what's different about the treatments and see if it, with a lot of data, does it predict a different outcome or is it still not discoverable from all of that data? It's too fine-grained. It's not present for the AI to figure it out. Okay. There is another question that I'm a little worried I'm going to misread it from Jim Dobbins, that given that the database is large and it's been in place for about 10 years, it hasn't been that large for very long. My slide was out of date from last month. It was 12,000. This month it's 15,000. So, and there have been algorithms that have already been created for severity prediction, and those predictions been graded for accuracy. I'm not sure about what are the severity predictions that there are algorithmically. So I didn't know if you could say more about that, or Dr. Vasilis, if you know what that's a reference to.
There are definitely tools out there that do GMFCS prediction, for example, based on factors. I don't know their performance off the top of my head, though.
I do think, yeah, and I guess what I would say is the example that's given in the second part of this, we do use our data to validate. So there were these GMFCS growth curves that were made for children with CP, different for boys and girls and different levels of GMFCS. And those were done with like 750 patients from I want to say Kaiser, or maybe 2,000 patients. We're validating those data with our large data set. So the idea of validating things that have done before is definitely something we will be doing. So to your point, June, yes, this does mean there will be committed to long-term follow-up for verification, like that advantage that Dr. Vasilis was just describing of not being held to some kind of funding 2-year outcome and being able to have long-term outcomes. We will definitely have that. Let me see if there's any other. I think that's it, Christy. I'm trying to see. Not sure if I know how to answer your question there about Zach, can you read Christy Bjornson's question and see if you feel like you can answer that? The second to last question.
Yeah, about gait analysis.
Yeah.
I know because we have done not gait analysis because we study babies, but just this idea of using video to recognize basically the way they work. This is called computer vision. They recognize where the body is in space. The algorithm can figure out this is the head is here, that's the left hand, this is the right hand, this is the elbow, the shoulder, and it draws a skeleton on top of the video essentially. And then as somebody moves in the video, as they're walking, for example, it tracks the angle of all of those parts together. So it can measure all the different parts that go into a gait analysis and do it in a very automated fashion. We've done that for babies with seizure detection, so trying to pick up seizures on a computer video screen. just by looking at the baby. There are people interested in neurologic exams, like being able to just take a video of someone and put it through an AI, and it does an automated neurologic exam using just the computer algorithm alone. So that kind of information could definitely be an input to a system like this. The whole deep learning system we described in the grant is really modular. We have the MRI module, we have the clinical data module, genetics data module, and these are individual add-ons. So we may not have that information for everybody, but I think the best algorithms really are built on sort of a baseline analysis with a minimum set of data. And then as you add more things, it just makes it better and better. So if you can add the gait analysis on top of the clinical data and the imaging data, the MRI, then it just gets that much better.
That's great. Well, I want to thank you, Dr. Vasilis, for your work and your commitment in this area. You're really kind of leading the charge for CPRN in what we're doing with machine learning, and I greatly appreciate your commitment and time to that, and then taking the extra time too, to answer questions. And I really appreciate all of you tuning in, giving your feedback. This is going to arm me a bit as I go into this NIH workshop that is about ethics and AI, to feel like I'm representing the community's view of some of these key questions. So thank you all for your time tonight. I greatly appreciate it. If you feel like something comes up about it afterwards, feel free to shoot me mail at paul@cprn.org, and I will be glad to reach out to Dr. Vasilis if I don't know the answer, or get an answer from wherever is appropriate. So thank you all. Have a good evening.
Thank you, Dr. Vasilis.
Bye.
Thank you.
Thank you.